Good evening. Welcome to video lecture 5F. In the last lecture, we constructed a generator matrix for a cyclic code with the identity matrix appearing on the right. And from this generator matrix, we constructed a PCM for the cyclic code in standard form. We saw that the syndrome of a vector with respect to this PCM can be obtained by dividing the vector by the canonical generator and taking its remainder. We also saw that the syndromes of a vector and its cyclic shifts are closely related. In today's lecture, we'll define the cyclic burst error correcting capability of a code. The codes and decoding algorithms we've studied so far are good for correcting random errors. More precisely, suppose that the underlying communications channel is a binary symmetric channel. We assume here that every bit of code word that's transmitted has the same probability p of being received incorrectly and probability 1 minus p of being received correctly. For example, if the code is a binary code of length n, and let's say its error correcting capability is 3, then if at most 3 bits of a code word are flipped during transmission, let's say these 3 bits that I'm choosing randomly, then the decoding algorithm is capable of making the correct decision. If 4 or more bits are flipped during transmission, let's say these 4 bits, then the decoding algorithm might make an incorrect decision. In practice, though, even though it's reasonable to assume that errors occur at random, when an error does occur, it tends to affect many coordinate positions of the code word that are close to each other. This might happen if code words are being transmitted through space and an electrical disturbance causes errors in many bits that are close to each other. Or perhaps the code words are being stored on a disk drive and a small scratch on the surface of the drive affects many bits close to each other. So in practice, even though errors do occur at random, when an error does occur, it tends to occur as a burst, which means that many bits close to each other might be affected. It might appear that codes designed for correcting a relatively small number of random errors per code word are not good at correcting bursts of relatively long lengths. However, we'll see in the next lecture that codes that are good at correcting a relatively small number of random errors per code word can be easily modified to give you a new code that's good at correcting burst errors of relatively long lengths. We'll also see in the next lecture that cyclic codes are good for correcting burst errors. Let me define cyclic burst errors more formally. We'll let E be a vector of length n. The cyclic burst length of E is the length of the shortest cyclic block of E that contains all the non-zero components of E. For example, the cyclic burst length of this vector E is 7. And that's because the cyclic block, beginning with the second last bit of E and continuing from the first bit to the 5th bit, contains all the non-zero entries of E. And furthermore, no shorter cyclic block of E contains all its non-zero components. The linear code C is a T-cyclic burst error correcting code if all cyclic burst errors of length at most T are in different cosets of C. In other words, have different syndromes. The largest such T is called the cyclic burst error correcting capability of the code. This definition makes sense because the received vector is in the same coset of C as the error vector. And so, if we want to use the code C to correct all cyclic burst errors of a certain length, then all those cyclic burst errors must lie in different cosets of C. Here is an example of a cyclic burst error correcting code. Let g of x be this degree 6 polynomial that we saw in the previous lecture. G of x is the canonical generator for a 59 binary cyclic code, which I'll call C. In fact, C is a 3 cyclic burst error correcting code. To check this, we need to verify that all cyclic burst errors of length at most 3 have different syndromes, and therefore lie in different cosets of C. This is a tedious calculation to do by hand, and so it's better done by a computer program. Nonetheless, I've written in this table some of the cyclic burst errors of length at most 3 and their syndromes, which you can see from their integer representations, are all different. There's a single cyclic burst error of length 0, namely the 0 vector of length 15. Its syndrome is a 0 vector whose integer representation is 0. There are 15 cyclic burst errors of length 1, namely the unit vectors of length 15. We have 15 cyclic burst errors of length 2. These are the vectors of length 15, having two 1s that are side by side. 15 cyclic burst errors of length 3, having a block of 3 1s, and 15 cyclic burst errors of length 3, having a block 1 0 1. In total, this gives us 61 cyclic burst errors of length at most 3. Now, there are 2 to the 6, which is 64 different syndromes. And so there are at least as many syndromes as cyclic burst errors of length at most 3. And luckily for us, the cyclic burst errors all have different syndromes. In practice, one finds cyclic codes with large cyclic burst error correcting capability either by a computer search or by using Reed-Solomon codes, as we'll see in Chapter 7. Here's a second example. This polynomial g of x of degree 8 is a canonical generator for a 15-7 binary cyclic code, which I'm calling C. The code C is a 4 cyclic burst error correcting code, as can be verified with a very tedious hand calculation. This is better done with a computer program. We next have a theorem that gives us an upper bound and a lower bound on the cyclic burst error correcting capability of a code. Let C be a linear code of length n, dimension k, and distance d over GFQ. And let T be its cyclic burst error correcting capability. Then T is at most n minus k and at least d minus 1 over 2. Let's prove the lower bound first. Recall that the vectors of weight at most d minus 1 over 2 lie in different cosets of C. In particular, all cyclic burst errors of length at most d minus 1 over 2 are also vectors of weight at most d minus 1 over 2, and hence they too must lie in different cosets of C. It follows that T is at least equal to d minus 1 over 2. Let's prove the upper bound on T next. Now, since C is a T cyclic burst error correcting code, no two cyclic burst errors of length at most T lie in the same coset of C. In particular, no two vectors in which all the non-zero components are in the first T coordinate positions, like this vector, can lie in the same coset of C. And this is because vectors of this form are also cyclic burst errors of length at most T. Now there are q to the t such vectors over GFQ, and q to the n minus k cosets of C. And hence q to the t must be no greater than q to the n minus k, from which it follows that t is at most n minus k.
We're ready now to introduce the decoding algorithm for cyclic burst error correcting codes. This we'll do in V5g. We'll also see a technique called interleaving, which can be used to increase the cyclic burst error correcting capability of a code. See you in V5g.